reflection coefficient in time domain, you have this one, right? Yeah, and then convolve with the wavelet, and then you have this one, right? So in time domain, we call it, this is in time domain. So when you do the, have you heard about fast Fourier transform? Fourier transform. You know, huh? That's to convert from time domain to frequency domain. So we call it fast Fourier transform to the frequency domain. Frequency domain. So the reflectivity in terms of frequency domain, you will see like this. Yeah. So when wavelet in the time domain, in the frequency domain, you will see like this. This is from this one to amplifier. Yeah. This one in the time domain to frequency domains become like this. Because this one multiplied by this one. You know something missing? Because the wavelet as a filter, it missing the low frequency one. This one is missing. So when you convert without low frequency model, this low frequency model is to capture, to rectify this information missing. That's why we need the low frequency modeling. The low frequency model can be from velocity, yeah, can be from velocity or can be from well-log data. Yeah. So from this operation, we know that because the Earth acts as a filter, it missing the low frequency, and this come up with the interview question. That's why we call it seismic is band limited because of this filter, Earth filter. The frequency band is band limited.
The Earth absorbs the.
Because of missing the low frequency one.
So the low frequency is missing because it has been filtered by the Earth.
The Earth, but yeah, filtered by Earth, so it's missing. We need to rectify by putting another information, seismic velocity or well-log data to rectify the low frequency model. So when you use that seismic velocity to and the log data, you will get a complete frequency spectrum. The low frequency will be rectified. Yeah. Okay. Why is different? I don't have the VPBS here. So AI sim formula is what?
Velocity.
VPA time
Density.
density. Tolong. SI is repeated. Yes. Time density, right? If my AI divided by SI, what we have?
VPBS.
Yeah. We have VP over berapa?
Velocity.
Ya.
VS velocity juga.
Big itu shin.
VP.
Betul. Empat.
VP itu velocity.
AI equal to VP times density, right?
VP itu apa Pak?
Oh, P velocity sonic. VP velocity of compression.
Oh.
Hey, you don't know VP, ya? What you call it normally in Canadian?
Apa ya Pak?
Hah?
Saya tak pernah buat Fourier transform FWI.
Oh, really?
Ah.
No one telling you about the fast Fourier transform?
Sebab dia susah.
It's a signal analysis lah. So if we have time, we can go to that one.
Tapi
But
S-wave punya DS tu S-wave punya
S-wave punya velocity.
shear impedance equal to Vs times density.
S
Shear. 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 S-H-E-R. Sini can follow.
So kiranya Pak, kalau MWI tu orang buat sebab the absence of low
So you
frequency
need
lah.
to
Full
insert the
waveform
seismic
inversion.
velocity to do the low
Full waveform inversion.
Okay.
This is important again. The updated technology in seismic processing, we call it full waveform inversion. Full waveform inversion itu dia dina algorithm dia to replicate the source signature.
Okay, thank you.
Okay.
When you replicate the source signature, your recording gathers will be mimicking the real seismic gather. That's we call it full waveform. Full waveform
Inversion.
inversion. It's different with the seismic inversion that we are teaching here. The full waveform, like for example, you have a full waveform, boom, you have full waveform.
Okay.
You know the spherical divergence, remember? Right?
From the source.
Yeah, from the source, right? Full waveform inversion is like back calculate to replicate the source signature itself. So you will have the source recording the same with the actual.
So part full waveform inversion, the result is more or less
Wait, Jihan.
the from full waveform inversion, the result is like we are actually looking at the seismic rate in our subsurface in real time. Is it?
Not real time, you can.
I mean, like real time using the actual one.
Yeah, you have a original raw data, right? The full waveform inversion is basically mimicking the raw data. The raw data sometimes have a noise, right? But in the full waveform, you can reduce the noise because you are modeling it. You can add the noise, increase the noise level, yeah, to mimic. But why not? Why we add the noise? We don't want the noise, right? So in the full waveform inversion, we will back calculate through the many algorithm lah. The velocity, density. The velocity density will be more detailed in the full waveform inversion. That's the algorithm lah in the full waveform.
Terus main produk kan. Tapi
So how do we get an analysis like
how the model yang cantik tu kita
we can drop like from the data.
tapi sekarang nak tanya saya
You making the source signature.
Yeah, depending the source signature. Like when we then
Has one.
to the source.
FFK is what? FFK is what? FFK is what? Fast.
More complicated way, the algorithm.
Fast Fourier.
But you start with the full waveform. When you full waveform inversion, when you have full waveform, right? You have a signature, right? It's a back calculate, invert the signature. So when you this is basically this is common sense lah. See? The common sense, you have full wave, right? Full waveform. Apa like that? Yeah. So you have when you travel, you hit the interface, you either reflected
Wavelet tu dah bagi.
Bounce back or
or
cancel.
transmitted. Correct. Not cancel. Why cancel? When you have a wave and then either you reflect or you transmit.
we create the low frequency model.
Some is
It's not
Absorb,
recover
yeah,
the low frequencies.
but not totally cancel.
Mungkin daripada
Absorb, yes, but some of the wave fast transmitted. Alright. Then you have a signature here in your geophone or in the hydrophone.
Create the low
You have this
frequency
one, right?
model.
Trace. Right? From this trace, you involve what? VP, VS, density. So when you iterate this one, this interface, you will get this wavelet, the signature, the source signature here. You iterate this information, that's the common sense. But the algorithm is much more complex.
So it's not, the algorithm probably cannot be done in Excel.
No.
Software.
No, cannot.
Oh, so only software is better.
Because of the complicated algorithm, the math.
Just understand like algorithm they usually like, okay, let's say like a graph. Instead of a straight curve, usually some of this graph they might have a curve, usually the so-called the mathematical model.
In MATLAB can.
In MATLAB can.
In MATLAB can.
Oh, okay.
But in Excel is too simple.
Oh.
You can do it in Excel, but
But I guess the data will crash.
yeah.
Oh,
And then
okay.
also the inversion, that what we will do, the exercise, is because of Excel cannot accommodate.
Even with the add-ons, it cannot.
With the add-on, can.
Okay.
Okay.
So,
But
does it involve a lot of like forecasting?
not forecasting. The forecasting is like stock.
Or
It's predicting the. It's like looping. Interesting. It is faster using AI now. It's faster. Hey, Rina, the FWI using AI now? Did you
AI like
validate using that? Belum, not yet.
we AI we talking about artificial intelligence, right?
Yeah.
Okay.
Yeah. Oh, not acoustic impedance.
Pak, one last question, Pak. For the previous one, to rectify the loss of the low frequency, we create a low frequency model.
Yeah.
For how do we create the
That's a good question. Next slide. So this is the rock physics lah. So first, some of the well don't have PS, the shear wave. This is PS, or we call it DTSM. Yeah, delta transmitted shear module. So the black one is the original, the red one is the predicted. So you can see from the predicted, of course there is overlap, and then we do the cross plot now to calculate the similarity. You do the cross plot. VS original, VS synthetic, the cross plot is 0.9 something, meaning your prediction is 2 times. Yeah. And then I calculate, this is the raw physics, P wave and density, right? So you do the cutoff, yeah. You do the cutoff for the sand and shale. So this is the line for the VP density, we call it Gardner relationship. For the VPVS, the famous one, the Greenberg and Castagna, both for sand and shale, because the area is plastic means sand, shale, yeah, clay or silt. So this is the viola basically. Which class is this? Daher. This one, which class? Oh, I already put. This is the real case using the OpenShell software. Yeah, you can do the same with Excel. If in Excel you do the average, remember we use the same average, share average. In this one, we all use complete log, but we only this one, synthetic from the log. From the log, you can get the synthetic velocity equal to lambda divided by frequency, correct? Yeah, 80 divided by 30. How much is this?
2 point.
2.9 7.
6, 7. 2.6 kilometer berapa second? Yeah. So that we can back calculate now. Okay. Now, in the feasibility analysis, this is basically yep, sonic clock. Sonic clock normally in microsecond per feet, right? So you have to convert to meter per second, become VP. Yeah. So you have VP, you have VS, you have density, right? If your VP divided by VS, you will have a VP VS lah, right? And then your VP times density, you have AI. So you cross plot VP over VS, you will get the this plot for lithology. Yeah. This is in time, this is in depth. This is in depth. Log resolution. This is 2 times seismic resolution. Then you summarize lah, well tie, how much the well tie, AVO, which IVO, and then visibility analysis, tuning thickness, and then well tie. This is well tie lah, basically. So you make sure your peak seismic equal to peak your synthetic, your trough seismic align with your trough synthetic. Yeah. Okay, this is the wavelet lah. So you see, this is headache lah. You have to extract every well in the 3 different interval and then average it all together. Yeah. So this is all the shallow, mid, and deep, right? And then this is the average. Okay. That's the average. So this is near, mid, far, ultra far. The average from this. This is headache lah, another headache. Extra average. And then you have this kind of nice wavelet. Yeah. Okay. This is low frequency model. Jivan. So we need to do the rock physics relationship because the seismic velocity equal to VP. Yeah, the seismic velocity equal to VP. So your VP, you convert P impedance and P wave. You have AI. Yeah, you have cross plot SI and P wave. You have this relation, and then you have density. You have this relation. Why I choose the AI, SI, and rho? Because the output of the pre-stack inversion, you have AI, SI, and rho. So we need to have to generate low frequency model relationship for this parameter. That's why I come up with this lah. Okay. And then so this is in the section from the log cross plot applied to the seismic velocity. Yeah. All right. And then when coming back again to the you have wavelet, you have low frequency, right? And then do the inversion. The QC of inversion, of course, compare between your well data and low frequency inversion. So it should be follow the trend of your AI, SI, and rho log and seismic. The log is in the black, seismic is in the red. So I do the cross plotting, QC all the wells, yeah. QC all the wells. This is the cross plot lah, basically, to measure the similarity. Yeah. And then this is the blind well. I'm surprised, oh, the blind well is good. And people also, hey, what did you do? I didn't do anything. This is the result. Okay. This is the section AI relative. This is absolute, meaning no with low frequency model. when they say relative without low frequency model. So you will hear AI absolute and AI relative. AI absolute with after adding low frequency model. AI relative before adding low frequency model. Okay? So you will have SI absolute, SI relative, rho absolute, rho relative. This is PPVS absolute. This is PPVS relative. Yeah. So this is the example. The comparison between inversion technique and simultaneous inversion. Yeah. This is with other inversion. Yeah. The scale is different. When you have a simultaneous inversion, your AI log and the AI inversion the same range, dynamic range. When you see in the other inversion, different ranges. Alright, so you can see that the difference between this one and this one. Yeah, the process this has been noise reduction. This is not reduce the noise yet, yeah, because the data comes before. This is after. You see the difference, huh? You see different or not? You have 1, 2, 3 missing this one, huh? You have missing this one in this section, missing layer. In this one, you have 1, 2, 3. So this is continuous. Like this. Or no? Yeah. This is missing, right? After this and then gone, and then other we have here small. But in this part we have nice.